I mentioned before that one of the tip-offs that an elimination reaction was taking place was the presence of heat under the arrow. And basically, if you're heating up a reaction, that's a sign that one of your products is likely to be an elimination reaction. And you might have wondered why that was the case. Why does heat tend to favor elimination products? Well, the answer really comes down to this equation right here. So if you took Chem 190 or you've had Chem 120, you'll recognize this as a Gibbs free energy equation. And delta G basically is a measure of whether a reaction is spontaneous or not. The more negative this number is, the more likely a reaction is to occur. And there's really two components to it. There's an enthalpy component that to an organic chemist really reads as bond energy. How much energy is associated with the chemical bonds you're making or breaking. So for instance, in order for this reaction to take place, we have to break a chlorine bond, and then we end up removing another hydrogen bond, but we end up making HCl. What we're doing here is we're generating new products that have different bond energies. And so if you sum up all the products and you subtract all the reactants from it, then what you get is a measure of the total energy. And the lower that energy is, the more negative that energy is, the more likely a process is to go forward. If the reaction is down in energy in terms of chemical bond energy and the redistribution, then the reaction tends to take place. But there's another term here, entropy, and what that essentially amounts to is a measure of the randomness of the universe. And what you need to know is that the universe tends to like to be random. There tends to be a lot of chaos. And so that term right there is essentially a measure of how much chaos is present. And so if you have a lot of small molecules that are generated, for example, HCl, then that tends to increase the randomness, especially if when we heat this, we drive that off and it evaporates, then that really increases the randomness of the universe because we have now generated a gaseous product. And so basically, if you think in terms of what the likely products are when you do an elimination reaction, you're almost always making at least some smaller molecules. You're taking some larger molecule and you're fragmenting it and you're making smaller molecules, which means that there's more chaos in general on the product side. So the entropy number is always a positive number, but this number gets bigger as you have more products. This number, the entropy number, becomes larger as the chaos goes up, as the number of products goes up, as the number of gaseous products that goes up, the number of small products goes up. So anyway, this number that relates to the chaos of the products, how many small molecules, how many gaseous molecules you made, that number gets larger on the elimination side in almost all elimination reactions. This will almost certainly have higher entropy than your reactants, which means that this is almost always a favorable term eventually. And since you want the delta G to be negative in order for the process to go, you will notice, of course, the presence of this temperature term. So the hotter the temperature, the more important the entropy part of this equation is, the relatively less importance the bond energy side of this equation is. Since eliminations almost always lead to higher entropy than you started with, if you tend to heat it up, then this term becomes more important, and that tends to make the elimination reaction more likely to happen versus substitution reaction, which essentially depends more on the bond energy term and less on the entropy term. Why does heat favor elimination? Largely because of the entropy term, and also because of the ability to remove things from the system. One of the things that's going on in many elimination products, not the one I have drawn here, but let's change this slightly. Let's say I'm trying to eliminate tert-butyl alcohol. And now let me change the solvents a little bit. We're going to do this in benzene as the solvent. We're going to use sulfuric acid as the reagent that turns that into a better leaving group. We're going to be heating it up, probably not with a Bunsen burner, but that's illustrative. And we're going to add something that we call a Dean-Stark trap here. This is a piece of apparatus that I've illustrated over there. I would now like to highlight that we're not going to be generating HCl at all, but what we will be generating, the thing that will be coming off on the far side, is water. So again, this is an illustration of the fact that elimination as a reaction almost always generates small molecules. Frequently water is one of the byproducts that we generate. So here we have sulfuric acid. That causes this to become a better leaving group. It then leaves, and then something comes along and deprotonates. We've now generated water. We're now running this reaction in benzene and we're heating it, and we have a Dean Stark trap on top. So here's my round bottom flask. I've got benzene and water both present. The benzene is the black, the blue is water, so they're all kind of mixed together. It's benzene and water, and we're heating it up, and that causes this to go into the gas phase, and it comes up into this condenser. So what I have here is cold water that runs through the condenser, which means that the vapor comes up here and condenses down and goes down into this finger. And what happens is that the benzene and the water tend to separate out. And so while I'm heating this and there's not much water present, a little bit of water can be dissolved. But once you have two phases in what looks like a SEP funnel, you have water on the bottom and you have benzene on the top. And so what happens is they separate and the water concentrates right here and the benzene fills up and then flows back down into your larger pot. And so over time, what happens is all of the water that's in this system ends up coming out. And what's left behind is essentially the benzene. What we're doing is a continuous extraction where we're removing all of the water from the system because the water and the benzene come up, condense, they separate, the water stays put, the benzene goes back down, and over time we enrich the pot in benzene. Said another way, what we're really doing is causing all of the water to go away. So we're removing water as a product. If you're familiar with Le Chatelier's principle, what we're doing is driving this reaction to the right because we're removing one of the products. The equilibrium, then it will shift to make more products. And so what we can essentially do is drive off all the water present. If we have tert-butyl alcohol, we simply run this trap until no more water is being collected, and then we know that all of the water in the system is gone, and what we're left with is the pure elimination product. Or at least that's the idea. So if you see sulfuric acid, if you see benzene, if you see Dean Stark, if you see heat, all of those are indications that an elimination reaction is taking place. And the main reason why an elimination is favored when you heat things up is the entropy term in the Gibbs free energy equation. Almost certainly eliminations are leading to more randomness. Therefore, that entropy term is going to be favored.
By which I mean the entropy term will take on greater importance relative to the enthalpy term in the Gibbs free energy expression.
In the presence of higher temperatures.